Good morning, chemistry students. Today we're going to learn how to determine the formula for an ionically bonded compound using electron dot diagrams. Now we know in ionic bonds that these compounds do not form molecules, they form crystals, and we're looking for the lowest ratio of one element to another. Now in nature we know there will be millions and millions of atoms of one element come in contact, usually right at the surface, with another element, and they would react and combine and bond, but we're going to look at the lowest ratio. So if sodium came in contact with fluorine, now there are millions and millions of these, or billions, but we're going to look at the lowest ratio, and how we would do that is we would determine the electron diagram for sodium. We know it's right there. It's an alkali metal, and so there's one valence electron. And we have fluorine. It's a halogen, so it has 7 valence electrons. So we would start out by just drawing one each of these and draw the electron dot diagram. Sodium has 1, and fluorine has 7. These nonmetals tend to be able to attract electrons due to their strong electrostatic charge, and they can attract electrons away from the metals who don't have as strong of hold on their electrons. And that is one of the main periodic trends. The more metallic something is, the further left and down on the periodic table, the weaker the hold on the electrons. The further up and to the right on the periodic table, the stronger the hold. So right here we'd have cesium is very weakly holding on to its electrons, and all the way up to fluorine is really attracting, and the noble gases have a very, very strong hold on their electron. So right here, sodium, fluorine wants 1 to fulfill the octet rule and to become stable. Sodium tends to give 1 away. And so what will happen is you will have a positive sodium ion and a negative fluorine ion. These opposite charges will attract, forming that crystal matrix that you saw on the interactive. Since we only needed 1 sodium and 1 fluorine to make them both stable, then our formula would be NaF. The subscripts you would put if there was more than one of either of those, but there's only 1, we assume we don't have to put a 1 there, we just assume. So if you don't see a subscript, then you can assume there's 1 atom. And this turns out to be overall neutral. Sodium had a positive 1 charge and 1 ion, so it contributed a 1 plus charge. Fluorine had a negative 1 charge, and there was 1 ion in the formula, so it had a negative 1 charge. What this results in is a neutral compound. There was 1 negative for each positive, so we don't have to write the ion notation when it's in a compound. It is neutral. This is sodium fluoride, and that is what is in your toothpaste. Let's do another example because people wanted some different examples. So let's say I was going to figure out the lowest ratio for calcium and chlorine. Well, I would start out with doing the electron dot diagram for each of them. Calcium is the alkali earth metal, so it has 2 valence electrons. And chlorine is a halogen again, and it has 7. So calcium has 2, chlorine will only attract 1 away because it doesn't want 2, it only needs 1 to make it to 8 to be stable and to fulfill the octet rule. So what's going to happen is the other electron from calcium will be attracted to a different chlorine molecule. Remember, we are exposing big lumps and billions of these different elements to each other. So now this chlorine is satisfied, this one's stable, and the calcium has given away both of the electrons from its outermost energy level. And so all 3 of these are more stable. And we have 1 calcium to 2 chlorines. So how we'd write this is CaCl2. The metal always goes first, the nonmetal always goes second. You do it left to right, just like on the periodic table. Metals are on the left, nonmetals are on the right. To make it, let's double check. Calcium tends to give away 2 electrons. So that's a +2, and there was only 1 of them in this formula. And so they would end up with a +2 charge. Chlorine tends to gain 1, and so it's a -1 charge, but we decided we need 2 of them. And so we'll end up with a -2 charge. So calcium +2, chlorine -2, equal and opposite, it is neutral. We have the same number of positive charges as negative. These are all combining together to form a crystal. And this is rock salt, calcium chloride. Let's try a different situation, sodium and phosphorus. I started out with my electron dot diagram. Sodium has 1 valence electron, phosphorus has 5, so sodium will give 1 away. Sodium's good, but what about phosphorus now? Well, phosphorus still needs to attract 2 more electrons to become stable. So what are we going to have? Well, we need, for every 1 phosphorus, we need 3 sodiums. So this would be Na3P. Na3P. So Na, the sodium would have a +1 charge, and there's 3 of them, for an overall +3 charge. The phosphorus has a -3 charge. That means it gains 3 electrons. Whoa, look at me go here. A -3 times 1 ion. And it has a -3 charge. So, sodium +3, the phosphorus is contributing -3. It's a neutral compound called sodium phosphide. And let's go on to a tricky one I don't have. And this is aluminum, Al, and oxygen. Why don't you stop the tape and see if you can figure out what the aluminum and oxygen, what the compound would form. That lowest ratio. So stop right now and boom, 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 boom. All right, I guess you're ready. Let's check it out. What I did was I had 1 oxygen and 1 aluminum, and that oxygen took 2 of the electrons from this aluminum. Now I had to keep on going. So there was another oxygen, and that last aluminum electron went to this second oxygen. And that's how it looked up to that point. But then I was like, well, this oxygen needs 1 more. So I put another aluminum. And remember, you have as many as you want. We were just looking for the lowest ratio. This would be billions of aluminum atoms and lots of oxygen molecules. And then the last 2 will go over here. So then I'll double check. This oxygen has 8, this has 8, this has 8. This aluminum's given away 3. This aluminum has given away 3. And so I would have Al2O3. Let's see if I'm right. Al2O3. It is a neutral compound. The aluminum, each of them had a +3 charge, and I had 2 of them, so that's 1, 2, 3, 4, 5, 6. Each oxygen has a -2 charge, and there's 3 of them, 1, 2, 3, 4, 5, 6. So it's a neutral compound of aluminum oxide. And we can count those up if we would like to. So go ahead and try LIS and see how you do. And then we will check it, stop it for a minute, check it, and then we'll keep going. Are you ready for the LIS? We had lithium sulfide. You needed 2 lithiums for each sulfur. I hope this helped you out. It was a little longer, but I had a request for more examples. So let me know if you have any questions.